Hey everyone, welcome back to the Lehigh Energy Systems Engineering Zoomcast series. This is the second Zoomcast of the semester where we cover Mr. Bobby Noble's seminar on utilizing gas turbines to meet our energy trilemma. Mr. Noble is the program manager for gas turbine R&D at EPRI. He received his BS in mechanical engineering from Clemson and MS in aerospace engineering from the Georgia Institute of Technology. He is an expert in the gas turbine field, with his primary fields of expertise being gas turbine combustion with a focus on combustion dynamics, high hydrogen and alternative fuels, and low NOx combustor architectures. He began his seminar by discussing the United States energy transition. The United States has set some ambitious goals to completely transform our energy system. Overall, the three major aspects of the energy transition is to make our energy system clean, affordable, and reliable. Within the near future, the United States is aiming to decarbonize electric generation, increase electrification, and make the grid more resilient against cyber and physical risks. Looking further out, within 30 years, the United States is aiming to achieve a totally net zero clean energy system. Owomu, would you like to discuss the progress we have made towards this energy transition?
We'll discuss the progress we've made in the energy transition and the future outlook for infrastructure development. The transition towards a more sustainable energy system is crucial for addressing climate change and achieving a cleaner and greener future. Let's start by looking at the progress we've made in terms of technology readiness level and the deployment of renewable energy sources. Technology readiness level, or TRLs, indicate the maturity of a technology ranging from 1 to 9, 1 being the early stage of a concept and 9 being a fully operational and proven in a real-world environment. The good news is that many renewable energy technologies have reached high TRLs levels, which means they are ready for a widespread adoption. For example, solar and wind technologies have made significant progress. Solar panels have become much more efficient and cost-effective, allowing for a greater deployment on rooftop and solar farms. Wind turbines, on the other hand, have also improved in efficiency and reliability, making them a viable option for generating clean electricity. As a result, we have seen a substantial increase in the deployment of these renewable energy sources around the world. To understand the growth of renewables, we can look at the S-curve growth dynamics showcased in the World Resources Institute, which states that the global electricity generation market witnessed a steady increase in the market share of solar and wind, growing at an average annual growth rate of 15% from 2015 to 2020. If this exponential growth rate persists, solar and wind could account for 45% of the electricity generation by 2030 and achieve 100% by 2033. These data demonstrate the positive trends with renewable accounting for a large portion of our energy consumption each year. This progress is driven by the advancement in technology, supportive policies, and public awareness of the need for cleaner energy. To address the emission from fossil fuel-based energy sources, the presenter emphasized on the importance of carbon capture and storage. CCS technologies capture carbon dioxide emission from power plant and industrial facilities, preventing them from being released into the atmosphere. The captured carbon is then stored underground, reducing greenhouse gas emission. The development and deployment of carbon capture storage infrastructure are crucial in achieving a low carbon future. Another important aspect of the energy transition is the development of and utilization of a low carbon fuels. These fuels, such as biofuels and hydrogen, produce fewer or no green gas emission during the combustion compared to conventional fossil fuels. Investing in the production and distribution infrastructure for low carbon fuel is vital for reducing emissions in the transportation sector, for instance. Now that we have a good understanding of the technology readiness of some of the technology we have out there, let's discuss the current state of infrastructure development and what it will look like in the future. The presenter emphasizes on the importance of developing a robust and efficient infrastructure to support the energy transition. Our current infrastructure predominantly relies on conventional fossil fuels, and such as coal, oil, and natural gas. However, as we transition to renewable energy and low carbon technologies, our infrastructure needs to adapt. This includes upgrading transmission and distribution systems to accommodate the integration of renewable. Additionally, the development of carbon capture and storage infrastructures and low carbon fuel distribution network is essential. In the future, infrastructure development will focus on expanding renewable energy infrastructure. This includes the construction of more solar and wind farms to harness the power from sun and wind. The development of energy storage systems such as batteries will play a crucial role in ensuring a stable and reliable supply of renewable energy. In addition, the integration of smart grid, advanced transmission systems, carbon capture, and low carbon fuel infrastructure will be crucial for achieving a sustainable and low carbon future. Lastly, infrastructure development will also focus on the electrification of transportation. Electrical vehicles are becoming increasingly popular. In the future, we can expect to see more EVs charging stations across cities, highway, and parking areas to support the widespread adoption of electric mobility. In conclusion, the energy transition is making a significant progress with renewable energy technologies reaching high level of maturity and deployment. Infrastructure development is a key component of this transition, and we can expect to see an expansion of renewable energy infrastructure, the integration of smart grid, and electrification of transportation. Thank you.
Thanks, Awomu, with that great description of the progress we have made so far. As mentioned previously, Mr. Noble is an expert in the gas turbine field. Mohammed, can you give us an overview of how gas turbines work and how they can help us achieve our energy transition targets?
Of course, Michael. Hydrogen gas turbine present a promising alternative to methane gas turbine and even renewable sources for clean energy future. Hydrogen turbine produce no carbon emission when combusted, making them cleaner option compared to methane gas turbine, which release carbon dioxide. This characteristic option hydrogen as a potential solution for decarbonizing industries and power generation. Hydrogen can produce using renewable energy sources through electricity process, providing a mean to store excess renewable energy when demand is low and use it when demand is high. Hydrogen has a high energy density, which means it can store a large amount of energy in a relatively small volume. This makes it suitable for application where space is limited, such as transportation and highly polluted area. When we are talking about the combustion configuration and technology, there are the conventional diffusion and combustion. This is the traditional combustion system where fuel is injected into the combustion chamber and mixing with it. It's typically used for all the gas turbine designs. They tend to produce high level of nitrogen dioxide emission compared to more modern design. The second one is the dry low NOx combustor are designed to minimize the formation of nitrogen oxide during combustion. To achieve this by controlling the fuel to air mixture and the combustion process. The dry low NOx system often use advanced fuel injection technique such as fuel staging to reduce NOx emissions. It's commonly used found in modern gas turbine engines for power generation. The third one is high hydrogen combustion technology. This technology focuses on utilizing hydrogen-rich fuel or hydrogen as a primary fuel sources. Hydrogen combustion offer as a potential for near zero emission of CO2 and NOx when produced using renewable energy sources. However, the challenging including the handling, storage, and the combustion characteristic of hydrogen, and for the performance factors that affecting the use of hydrogen, there are several factors influence the performance of hydrogen gas turbine, including combustion efficiency, turbine design, fuel purity, and operational condition. Effective management of this factor is essential to optimize performance and ensure reliability of operation. But when we are talking about the power output, hydrogen turbine can achieve significant power output, making them suitable for large-scale power generation application. Their high efficiency and low emission make them competitive with conventional fossil fuel-based power generation technology. So that hydrogen gas turbine offer a promising pathway toward a cleaner and more sustainable energy future by leveraging hydrogen environmental benefits, energy storage capability, and potential for economy-wide decarbonization.
Thanks, Mohammed, for that thorough analysis on gas turbines. Gas turbines powered with hydrogen gas are a great technology to help us meet our transition goals. However, with any emerging technology, there are challenges that must be addressed. Corey, can you go over some of these challenges and things we should consider as we start to utilize gas turbines?
Gas turbines play a crucial role in power generation, but they come with various challenges and considerations, including emissions, safety, misconception, limited research, and high implementation costs. To get a better understanding of the challenges and considerations, let's delve into the main types of fuels used by gas turbines. Natural gas is the main type of fuel used in gas turbines today, primarily composed of methane. When natural gas is burned in a gas turbine, it produces nitric oxides and high levels of carbon dioxide. The US Department of Energy aims for 100% carbon-free electricity by 2035 in alignment with the global climate goals. To decarbonize further, we should explore alternatives to natural gas. Hydrogen and ammonia are promising options. Hydrogen combustion offers near zero carbon dioxide and nitric oxide emissions compared to natural gas. However, there are trade-offs. Diffusion technology offers full-range nitrogen capabilities but high nitric oxide emissions. Dry low NOx technology produces low NOx but limited hydrogen capabilities. Next-gen dry low NOx technology produces full hydrogen capabilities and low NOx, but more research and development are needed. Then you have safety challenges with hydrogen. Hydrogen is prone to flashbacks in dry low NOx systems. Pre-mixed fuels increases the risk of flashbacks. Implementing safety measures and designing robust systems are critical for hydrogen-powered gas turbines. Compatibility challenges. Next generation dry low NOx technology offers full hydrogen capabilities and low nitric oxide emissions, but it faces compatibility issues. Compared to natural gas, hydrogen has different combustion characteristics affecting turbine components and materials. So ensuring compatibility with existing infrastructure and materials are essential for the successful implementation of hydrogen technologies. Fuel flexibility challenges for current gas turbines. Achieving fuel flexibility is a significant challenge. Designing a combustion system that avoids flashbacks when using hydrogen and prevent blowouts when using natural gas is not an easy feat. The primary reason lies in the difference in flame speed between these fuels. Dry low NOx challenges with ammonia poses its own set of challenges. The reaction rate for ammonia is 20% slower than that of natural gas, leading to slower combustion. Unfortunately, ammonia also produces high levels of nitric oxides due to nitrogen content in the fuel. In fact, ammonia generates 3 times the amount of nitric oxides compared to hydrogen and natural gas. Then you have cost considerations. When discussing costs, we must address several factors such as research and development, implementation costs, and transportation infrastructure. Implementing alternative fuels like nitrogen requires substantial research and development investment. And transitioning from current hydrocarbon fuels to cleaner alternatives involves expense related to equipment upgrades and modifications. The transportation infrastructure for hydrogen faces limitations due to the lack of widespread hydrogen transmission pipelines across the United States. Expanding this infrastructure is essential for making hydrogen a viable option for power generation. In summary, while hydrogen offers emission benefits, addressing safety, compatibility, and cost-related challenges will be crucial for its successful integration into gas turbine technology.
Thanks, Corey. Well, this sums it up for the second Zoomcast in the Lehigh Energy Systems Engineering Zoomcast series. I would like to thank Mr. Noble for making time to come in person and discuss how gas turbines are critical for our energy transition. Be sure to come back in 2 weeks for our third Zoomcast, where we cover Laura Marsoglio's seminar on the grid.